Quality assurance in the laboratory involves every factor that may influence a patient's treatment. We begin with pre-analytical variables. These include issues with specimen collection, the conditions and methods of transport, and the types of preservatives that are used. Errors at this stage can compromise the integrity of the sample before testing even begins. Next, we have the analytical variables. This is the stage of actual test processing. Here, quality control data becomes essential because it helps us monitor the accuracy and precision of the testing process itself. Finally, there are the post-analytical variables. These involve evaluating the test results, ensuring that reporting and documentation are accurate, and recording any corrective actions taken when problems arise. This stage also considers turnaround time, which is critical to patient care, as well as how complaints are received, documented, and resolved. In summary, quality assurance spans from the time a specimen is collected to the time a result is reported and acted upon, making it a comprehensive framework that safeguards patient treatment. Quality control definitions are essential when it comes to understanding lab processes. Let's start with accuracy. Accuracy is the agreement of test results with the true value for a substance in a specimen. Statistical measures of accuracy include the mean, or the average value, the mode, which is the most common value, and the median, which is the middle value in a distribution. Next, we have precision. Precision refers to the ability of a test to repeatedly produce results on the same sample that are very close to each other. This is also called reproducibility. Statistical measures of precision include the standard deviation and the coefficient of variation, which is sometimes called the relative standard deviation and is expressed as a percentage. To determine the standard deviation, a minimum of 20 analyses are needed. Precision also follows a normal or Gaussian distribution. In this model, about 68% of values will fall within plus or minus 1 standard deviation. About 95% will fall within plus or minus 2 standard deviations, and about 99% will fall within plus or minus 3 standard deviations. Next is sensitivity. Analytical sensitivity is the ability of a test to detect very small concentrations of a substance. Diagnostic sensitivity refers to the ability of a test to correctly produce a positive result if the patient truly has the disease. Then we move to specificity. Analytical specificity is the ability of a test to measure only the substance of interest, without interference from other substances. Diagnostic specificity means the ability to correctly produce a negative result if the patient does not have the disease. The reference range, also called the normal range, is the range in which 95% of the healthy population is expected to fall. Random samples from this normal population should fall within the mean plus or minus 2 standard deviations. A standard is a substance with a known concentration that yields a single assay value. Primary standards are chemically pure and can be directly weighed or measured. Secondary standards are less expensive and are calibrated against a primary standard or a reference method. A control is a substance with a known or determined range of values. If the values are provided by the manufacturer, the control is called assayed. If the values are not provided, the laboratory must establish the range, and the control is called unassayed. The confidence interval, sometimes called the control range, is the range of values within which control results must fall. This interval is usually established by analyzing the control at least 20 times, then calculating the mean, the standard deviation, and the plus or minus 2 standard deviation range. A delta check compares a patient's most recent result with previous results. If there is a large disparity, it usually indicates an error in one of the results, so both samples must be rerun. Proficiency testing, also known as external quality control, compares your laboratory's results to a large group of other laboratories analyzing the same samples. A measure called the Standard Deviation Index, or SDI, is often used. Another tool is the Uden plot, where Level 1 control results are plotted on the x-axis and Level 2 control results are plotted on the y-axis. A plus or minus 2 standard deviation box is drawn, and your laboratory's results should fall within that box. Finally, An individualized quality control plan is an optional program developed by each laboratory. It identifies potential sources of error in the pre-analytical, analytical, and post-analytical phases, and creates a tailored plan to reduce or avoid those errors. In summary, these definitions form the backbone of quality control in laboratory testing, ensuring accuracy, precision, and reliability for patient care. When we evaluate laboratory testing, it's important to recognize the sources of variation or error. First, there is random error. Random error can arise from several sources. It may be due to instrument problems such as voltage fluctuations or incorrect sample volume. It can also occur because of sample issues, such as anticoagulant interference, the presence of certain drugs, lipemia, or hemolysis. Finally, random error may result from human mistakes, like improper preparation or storage of control samples. Next, we have systematic error. Systematic error is different because it consistently shifts results in the same direction. It may come from instrument problems, such as a dirty photometer or a faulty ion-selective electrode. It can also result from the decomposition of standards or reagents due to evaporation or contamination. Systematic error may appear as a constant bias, where the y-intercept is not zero, or as a proportional bias, where the slope is not equal to 1. Now let's turn to method comparison. The t-test is used to compare the means of two populations, or two test methods, and it helps us evaluate the accuracy of one method versus another. The f-test is used to compare the standard deviations of two populations or two test methods, and it helps us evaluate the precision of those methods. Then there is method validation. This includes calibration verification, which confirms that instruments are properly calibrated. It also involves the analytical measurement range, sometimes called the AMR. This includes linearity, which is the reportable range, and the range of values for a procedure that may be reported without dilution. When interpreting quality control, several important concepts come into play. First is the idea of a trend. A trend occurs when values for the control continue to either steadily increase or steadily decrease over a period of about 6 consecutive days. Trends may suggest reagent deterioration or gradual instrument wear. These are best identified by visually inspecting a Levy-Jennings quality control chart. Next is a shift. A shift happens when 6 or more consecutive daily values fall consistently on one side of the mean value line, while maintaining a relatively constant level. A shift may be caused by deterioration of a standard or a change in reagent lot. Like trends, shifts are also detected by visually inspecting a Levy-Jennings chart. Now let's review the Westgard Multi-Rules, which help determine whether a run of samples should be accepted or rejected. The warning rule is called 1-2S. If a single observation exceeds the mean plus or minus 2 standard deviations, we evaluate the previous controls. If no other rules are violated, the run is accepted. The rejection rules indicate an out-of-control situation. 1-3S means a run is rejected when a single observation exceeds the mean plus or minus 3 standard deviations. 2-2S means a run is rejected when 2 consecutive observations exceed the same mean plus 2 standard deviations limit, or the same mean minus 2 standard deviations limit. R-4-S means a run is rejected when one observation exceeds the mean plus 2 standard deviations, and the next exceeds the mean minus 2 standard deviations, making the points more than 4 standard deviations apart. 4-1S means rejection occurs when 4 consecutive observations exceed the same mean plus 1 standard deviation limit, or the same mean minus 1 standard deviation limit. 10X means rejection occurs when 10 consecutive observations all fall on the same side of the mean. Now let's discuss reference ranges, or normal values. These ranges define the expected values for a constituent of clinical interest in a healthy population. They are established from groups of individuals free of obvious abnormalities and typically cover 95% of the normal population. which is equivalent to the mean plus or minus 2 standard deviations. Several considerations affect reference ranges, including race, age, sex, weight, nutritional and absorptive states, physical activity, body position during sampling, menstrual cycle, emotional state, geographic location, and even time of day because of diurnal variation. Analytical methods can also cause differences. When establishing reference ranges, it is best to use a large population, ideally at least 100 individuals from the community where the lab is located. The values for the analyte should follow a Gaussian or normal distribution. From there, the 95% confidence limits are determined as the mean plus or minus 2 standard deviations, understanding that 1 out of 20 healthy individuals may fall outside this range. In summary, quality control interpretation involves recognizing trends and shifts, applying Westgard rules to monitor accuracy and precision, and establishing reliable reference ranges that account for biological and analytical variability.